Water and wastewater treatment education in the environmental laboratory of the Vasa University of Applied Sciences. The focus of the education of the environmental laboratory in Vasa University of Applied Sciences is on water and wastewater treatment. In addition to ordinary jar test apparatus and the most common analytic facilities, we have a few laboratory and pilot-scale apparatuses that can be used to demonstrate the most common processes and operations on water and in wastewater treatment. In this presentation, we'll introduce our pilot-scale waterworks, benchtop electroflotation cell, pilot-scale membrane filtration unit, and benchtop wastewater treatment plant based on the activated sludge process. Here we have before us 2 glasses of water. On the left, a glass of water drawn directly from Kurun River, from which the city of Vasa takes its raw water. On the right, a glass of water that has been treated with our benchtop scale waterworks here at our laboratory at the Vasa University of Applied Sciences. The apparatus is fully automated by using PLC control and handles the following unit operations and processes. The first stage, clarification, is basically an aesthetic consideration, as we all know that people prefer to drink clear, transparent water. The second stage, disinfection, on the contrary, is fundamental. Removing of pathogens from the water is part of basic healthcare infrastructure. The third stage involves post-treatment to protect the distribution piping from corrosion. The color and turbidity of river water is caused mainly by colloidal-sized clay particles and humic substances. Although the density of these materials is higher than water, the particles do not sediment due to the small particle size. Chemical precipitation using iron salts encourages humus and particles to coagulate, forming bigger flocks that can be separated out. The first step involved in chemical precipitation is coagulation, the stabilization and initial coalescing of colloidal particles occurring on an extremely short time scale during the rapid mixing stage through the action of iron sulfate, the PIX 322 commercial product of Kemira. Flocculation is the longer-term process of growing larger particles from smaller particles formed by coagulation. During the low-intensity mixing in 3 consecutive basins, colloidal particles are bound to the resulting iron hydroxide. During the sedimentation, the iron hydroxide flocks entrapping the impurities are separated out by allowing them to settle to the bottom of a vertical flow clarifier. The flocks have a higher density than water and therefore tend to sink. The resulting sludge is pumped out from the bottom of the clarifier once every other hour. The rapid sand filter separates the remaining flocks, that is, those flocks that were not trapped in the clarifier. The sand filter is set to backwash with tap water and air at predetermined times, once every 24 hours. After the chlorination stage, the pH value is adjusted by sodium hydroxide and carbon dioxide in order to protect the distribution piping from corrosion. The unit operations and processes demonstrated by our benchtop version are the basic elements in all treatment systems of surface waters. Depending on the installation and local conditions, various other unit operations, for example, membrane filtration, may be included. As an alternative to sedimentation, clarification is often implemented by flotation. Flotation, in a sense, is the opposite of sedimentation. In flotation, the floc particles are induced to rise to the surface of the tank by entrapment of gas, usually air, within the mass of the floc. The resulting floc-bearing foam is skimmed off the surface of the flotation cell, and clear water is decanted from a lower level of the cell. In the laboratory of the Vasa University of Applied Sciences, we have a laboratory-scale benchtop flotation cell. However, it is somewhat unconventional as it uses electrolytically produced hydrogen and oxygen as the flotation gases. Due to this electroflotation technology, the apparatus is small in size, highly portable, and convenient for even classroom demonstrations. In real-life applications, the main advantage of the electrolytic gas production is the extremely small size of the gas bubbles produced. However, due to economic considerations, the technology is used at the present mainly in niche applications. Conventionally, filtration in water treatment refers to the separation of solid particles from water streams. Membrane filtration, however, extends this application to include the separation of dissolved solutes. Probably the best-known membrane filtration technique is reverse osmosis, used for the desalinization of seawater. It consists of forcing pure water with a high-pressure pump through a semi-permeable membrane that allows the passage of water, but not of dissolved salts. This process is not a simple sieve separation, but the main mechanism is diffusion of solution through the membrane. Other more common pressure-driven membrane processes are microfiltration, ultrafiltration, and nanofiltration, which can be classified according to the mean pore size of the membranes and the operating pressure. In the environmental laboratory of the Vasa University of Applied Science, we have a laboratory-scale membrane filtration apparatus, which can be used to demonstrate all of the above-mentioned techniques. Our apparatus is based on the cross-flow principle. In a conventional filter, flow is perpendicular to the filtering medium, and all flow passes through the medium. In a cross-flow process, however, the raw water is fed parallel to the filtering membrane, with only a certain proportion of the flow passing as a clear permeate through the membrane. Thus, rejected material tends to be carried with the reject water, enriching in the concentrate or being continuously removed from the filter module. One advantage of such implementation is that the flow is continuously flushing the membrane and hence retarding its fouling, that is, the accumulation of dissolved species at the membrane surface and in the pore. Our apparatus consists of a 30-liter feed tank, one centrifugal pump producing operating pressures up to 16 bars, 2 parallel lines of water flow, 2 parallel flat-sheet membrane modules equipped with pressure meters at both input and output ends, and a flow meter. The membranes can be easily exchanged as the flat sheet module is easily detached. The module consists of several components, and the filtration area is 68 square centimeters. In this demonstration, humic substances are removed from the raw water. We have a nanofiltration membrane in the front cell and an ultrafiltration membrane in the back cell. The humic containing brownish raw water is pumped from the feed tank through the membrane module and the flow meter and circulated back to the feed tank. The permeate is collected in measuring cylinders. As the membrane used in ultrafiltration is leakier, the permeate flow and, consequently, the flux is greater. However, nanofiltration removes a wider range of impurities.